Hello everyone and welcome to our new section which is called Stack. With this lecture, we begin a brand new section in which we will learn everything about stacks. In this section, you will get a deep knowledge about stacks, which includes creating stacks based on Python list and linked list and performing various operations like creation, pushing, popping on these stacks. Now in the first lecture, let's see what's a stack. So let's get started. The structure of stack can be imagined as a pile of objects stacked vertically. When extracting these objects, the last added to the stack is the first one removed. The real-life example for stack can be a pile of dinner plates, pile of books, or bangles in the hand. So for the explanation, let's look at the pile of dinner plates over here. If we observe the properties of this pile of dinner plates, we can easily see that we have a leaf method over here. This means that the insertion or removal of these plates follows the leaf method that is last in, first out method. Now what do we mean by that? Let's see. We can clearly see that this plate over here has been placed first, and then this plate placed on it, and then this plate placed on it. And finally, this plate is the last one which is inserted in the head of stack over here. Now if we want to take one plate from this pile of plates, we have to take the last plate from here first. Because if we want to take first plate, it's not possible because there are plates on this. So if we take the first plate, we will break all of them. So to take the first plate, we have to take all plates that are located on it, and only then the first plate can be taken. So here you see that whichever plates come last, it has to be taken first. So this plate over here is placed last, so it will be taken first. So this property is called leaf property. That's last in and first out. Similarly, the stack data structure follows the same property, that is whichever element comes in last, it has to be taken out first. So now let's quickly see example of stack data structure in computer science world. So here we have a stack which follows leaf method. So first we insert number 10 into our stack, then we insert number 20, then we insert number 30, and then we insert number 40. Now if you want to remove the number 30 from this stack, we cannot do it directly. It can be removed only when the number of 40 is removed from the stack. Because according to the leaf method, the last method has to be removed first. So to remove 30 from this stack, we need to remove first 40. Then now the 30 is the last element, so 30 can be removed from our stack over here. Then it continues like this, 20 and 10 at the end. So now hopefully you have understood what exactly is the stack data structure. Now let's see why we have a stack data structure and why do we need it. We need a stack data structure whenever we need a functionality in our application that utilizes the last coming data first. The classical example for stack data structure is back button in the browser. So here we have a browser and there is a back button on it. So the way that back button works is exactly follows the same principle of stack. So let's see, today first I browsed udemy.com. Then I checked my email using gmail.com. Then from email I saw that there's a notification from LinkedIn, so I visited LinkedIn. And finally, I visited my own website which is called appmillers.com. By the way, we are in the process of updating our website, which will have a lot of free programming tutorial in it. So if you are interested, do not forget to visit us on our website, which is appmillers.com. So currently we are on appmillers.com. Now what will happen if I click back button over here? It's clear that it will go back to the LinkedIn because this is the website that we visited before appmillers.com. So if I click back button one more time, it will go to gmail.com, and if I click back button one more time, it will go to udemy.com. So you see that whichever website comes last, it has been utilized first. So in our case, AppMillers was the last website that we visited, so it popped out first. Then LinkedIn comes in the second last place. Then after this one, Gmail, then we reach the first website that we visited, which is udemy.com. Now if we put these websites in stack formation, it will look like this. So first we visited udemy.com, then Gmail, then LinkedIn, and then appmillers.com. So when extracting data from this stack, the last one that we visited will be removed first. So we know that the last website that we visited is appmillers.com, so it will be removed first. Then the last second website that we visit is linkedin.com, so it will be removed then it will continue like this until we reach the first website. So as you see, stack data structure works the way that back button works in the browser. So back button in the browser is very good real example for stack data structure. Now this is all for this lecture, and hopefully you have understood the overall concept of stack data structure. Now in the next lecture, let's start learning the operations that we can perform on stack data structures, and let's learn how can we implement them. So see you in the next lecture. Alright, in the last lecture we have learned what's a stack and why do we need it. Now starting from this lecture we will learn common operations that we can perform on stacks. These operations include creation of stack, push method in stack, pop method in stack, pip method in stack, and isEmpty isFull methods and delete stack. So let's get started with creating stack. So to create a stack, we just need to initialize an empty list or linked list inside stack class without any element in it. Here we are not adding any element from the creation. We are just creating an object of stack class. So let's continue to the next operation. The next operation is push method. So right now we have an empty stack. So the first operation we'll perform on this stack is to push elements. So in the world of stack, when we say the word push, we basically mean to insert. But when we say the word pop, we basically mean to remove an element from a stack. So let's see how push operation works in the stack. So we have an empty stack over here. So when we insert the first element in the stack, it's located in the memory like this. And when we insert the second element, it will be located in the memory on the top of this element over here. So if we continue like this to insert third element, once again it will locate it on the top of other element, the one that is inserted last. Then finally the last element also will be located on the top of the last element that we inserted over here. Now we have inserted these four elements to this stack over here. And the elements are located on the top of each other. So here we have seen how push method works. So every time when we insert an element to the stack, the element will be located on the top of the previous element. So the next operation is pop operation. As we have already said in the world of stack, instead of remove we use pop over here. So here is the same stack that we inserted elements in the previous slide. So if we perform a pop operation on this stack over here, it will return the top element, which is 4 in our case. And after returning this element will be removed from the stack. Then one more time, if we perform pop operation over here, in this case it will return 3 and 3 will be deleted from this stack. And if we perform pop method over here one more time, it will return 2 because now the 2 is the last element that we inserted in the stack. So it will return 2 and 2 will be deleted from the stack. And finally, if we perform pop method one more time, it will return the last element and the last element will be removed from the stack. Now we have an empty stack. So if we perform pop method one more time, what will happen? So in this case, it will raise an error saying that the stack is empty. So when the stack is empty, we cannot perform pop method over here. Now let's continue to the next operation, which is pick operation. So pick operation is very similar to pop operation. The only difference is that the top element of stack will not be updated. This means that this method returns the top element from the stack, but the top element will not be removed. So if we run pick method for this stack over here, it will return 4, but 4 will not be removed from the stack. So if we run one more time pick method over here, it will return 4, but 4 will not be removed from the stack. So it doesn't matter how many times that we run pick method, it will return 4 in our case. But before pick method, if we run pop method, it will remove the 4. So then if we run the pick method, it will return 3 over here. This means that pick method always return the top element from the stack data structure. So you might be interested, why do we need pick method? So in some applications, we just might want to check the top element in the stack without removing it. So in this case, pick method is very useful. Now the next operation is to check if there is an element in the stack or not. So this method is called isEmpty method. So this method is used inside other methods to check element in the stack, because if there is not any element in the stack, it does not make sense to perform pick or pop method for the stack. So if there is not any element in the stacks, this method will return true, otherwise it returns false. So in our case, we have elements in our stack, so this means that our stack is not empty, so it will return false. Now let's continue to the next operation. The next operation is isFull operation. So in some programming language, when you create a stack based on the array, we need to define the size of array when we declare it. So it means that the size of stack will be limited. So when the size is reached, it means that it's full. We cannot push any element to this stack over here. Now in the case of Python list, we don't have any size limit, so we don't need this method when we create a stack without size limit. But if we create a stack with size limit, we need this method. So in this course, we will look at both cases. Now finally, the last operation is deletion of entire stack. So to delete an entire stack, we need to set list to an empty list. So in this case, all elements of stack get deleted from the memory. Now this is the last operation for the stack. So with this, we have completed this lecture. So in this lecture, we have learned different types of operations that we can perform on stack data structure. Now in the next lecture, let's implement these methods in practice using Python list. Alright, in this lecture, we will learn how to create a stack. So here we need to know that there are various ways of implementing stacks in Python. In this course, we will look at 3 cases that are using a Python list without size limit, using a Python list with size limit, and using linked list. Here the core logic is the same, but there might be slight differences between these cases. Now let's quickly review the differences between these cases over here. So implementing a stack using Python list is very easy, and this is one of the advantages of using a list for stacks. Unfortunately, list has a few shortcomings compared to linked list. The biggest issue is that it can be run into speed issues as it grows. So the items in a list are stored with the goal of providing fast access to the random elements in the list. So at a high level, this means that the items are stored next to each other in memory. So if our stack grows bigger than the block of the memory that currently holds it, the Python needs to do some memory allocation. And this is very time-consuming operation. On the other hand, implementing a stack using linked list is faster than a list in terms of performance, because the elements of the linked list are not located contiguously in the memory. So the memory allocation is not required in this case, when the data size gets bigger. The disadvantage of using linked list is implementation is not easy as the list. So these are the main differences between these 2 types of stacks. So here initially we will learn how to create and perform mentioned operation on stack using Python list. And then we will learn the same operation using linked list in the stack. So let's see how can we create a stack using Python list. So here we will create a stack using Python list in which we don't have any size limit. This means that we can insert as many as elements in this stack over here. But you have to be very careful with this case, because here you will have performance leaks as the size of list grows. So let's get started. So to create a stack without a size limit, we just need to create an empty list inside stack class. So class stack, and inside stack class, we will create init function, which will take self parameter. Then here inside init function, we will initialize our empty list. So list will be empty list. So with this, we are creating an empty stack over here. Now here, I will change the str function as well, because when we print out the stack, I want you to show it in proper way, as it was in the slides. Basically, what we are doing over here, we are just trying to print out our stack in the way that we showed in the slides. So each element will be on the top of the other element. That's why I just modified this str function over here. So now we have completed the creation of stack using linked list without size limit. So you might be interested what's the time and space complexity for this operation over here. So we know that when we create an empty list, it takes a one-time complexity. So because we are just initializing a list over here. And the space complexity obviously is 1 also, because we are not inserting an element over here. We are just creating the empty list in the memory. Now in the next lecture, let's implement stack operations on this stack that we created over here. So see you in the next lecture. So in this lecture, we will learn how to create stack methods for the stack that we created in the previous lecture. So the first method is isEmpty method. So we learned that isEmpty method checks that if the stack is empty or not. If it is empty, it is returning true. If it's not empty, it returns false. So we will declare our isEmpty method like this, isEmpty. So by default it takes self parameter. Then inside if condition we are checking if self.list is an empty list, it means that this stack is empty, so we will return true. Otherwise we are returning false. So let's create a stack and check that if this method works correct or not. So here I will create an object of stack class over here. So custom stack equals stack class. Then I will print out the isEmpty method. Now it should return true because now our stack is empty. So if we run our code, you see that it returns true over here, which means that our method works perfect. So now let's see what's the time and space complexity for this method. So the time complexity is O1 because here we are just checking if the list is empty list or not. And the space complexity is also O1 because here an additional space memory is not required to perform this empty method over here. Now the next method is push method. So to push an element to the stack in which we don't have size limit, we are just using Python list standard method which is called append method. So we know from our list section that the append method insert an element at the end of list. So here we will declare our push method like this, push self as a parameter. So it will call list standard method which is append, and this method will take value as a parameter. We need a value to insert in the stack, so it will take value. Then we will return saying that the element has been successfully inserted. As you see, if we don't have any size limit for the stack, the push method is very easier. We are just using the Python list's standard method which is append. So let's see what's the time complexity for this method over here. The time needed to append an item to the list is amortized constant. Whenever the list needs to allocate more memory, it allocates room for a few items more than it actually needs to avoid having reallocate on each call. So every time when it reaches the memory size, it will reallocate the memory. And this means that append method in the list amortized constant, so the allocation overhead may push behavior towards O(n) time complexity. Even in the worst cases, if we have more elements in the list, it might take O(n) squared time complexity. So the space complexity is O1 because here we are just appending one element at a time. So now let's see how this method is working over here. So here I will call custom.push, and here I will insert one. Let me insert few elements over here. Then after inserting elements over here, let's print out our custom stack over here. So if I save it and run it, you see that first we have pushed the number of 1, then we have pushed the number of 2, and then we have pushed the number of 3. As you see, each element is located on the previous one that we inserted. So the last one that we inserted is 3. So 3 is located at the top of stack over here. Now the next method is pop method. So here we know that pop method returns the top element from the stack and removes it from the stack. So here I will declare pop method like this, pop. The first thing that we are going to do, we will check if this stack is empty or not. If it is empty, we will return a message saying that there is no element to pop up. If it is not, we will pop this top element from the list. So here our first condition is like this: if self.isEmpty, then we return saying that there is not any element in the stack. Otherwise, as we said before, implementing stack using Python list is very easy. So here also we have another standard method which is pop method. So we'll use this standard method. So pop method of list is just returning the last element from the list and removing that element from the list. So in this case, it works perfectly for our case. So you might be interested what's the time complexity for this method over here. Once again, the time complexity is O1 and the space complexity is also O1 because here we are just removing one element from the end of list. So let's see how this is working. So here we have created custom list and inserted some elements to it. Then we pushed 3 elements to it. So after printing these, so if we run pop method for this stack over here, you will see that the last element that we inserted is 3, so it will remove the 3 and return 3. So if we run it, so the return value of this method over here is 3. So if we just print out the stack after this method, you will see that we have only 2 elements in this stack. So let's run it. You see that this is the one that we removed, then we have 2 elements over here when we print out this stack over here. Now the next method is pick method. So we know that pick method returns the last element in the stack. So here we will declare pick method. Then one more time we will check if this stack is empty or not. If it is empty, we will return message saying that there is not any element in this stack. Otherwise, we will return top element. So to return top element, I will do like this. Self.list, and inside parentheses, if we take the length of list and -1, this index becomes the last element in the list. So it will return the last element from the stack over here. Let's save it and run our code. So I will print out the value of this, the custom.pick. So if we run our code, so you see that it returns 3. So if we print out the custom stack over here, you will see that 3 still exists in the custom stack. So as you see, from the first print statement, it prints out 3, then the custom stack, then all elements are remained in the custom stack over here. Now let's see what is the time and space complexity for this method over here. The time complexity is O1 because we know that accessing any given element of list takes O1 time complexity. So when we access the last element in the list takes O1 time complexity. So that's why this method over here takes O1 time complexity. Now the space complexity is also O1 because here an additional memory is not required to perform this operation over here. Now the last method for this stack is delete entire stack. So to delete entire stack, we know that we need to set the list to empty list. So we need to set the list to null. So here I will create delete method like this. Then inside delete method, we will put self list to null. So by doing so, we are deleting all elements from the stack. So we have successfully deleted this stack from the memory. Now the time complexity for this method is O1 because we are just deleting all elements from the list. And the space complexity will be also O1 because here an additional memory is not required to perform this operation. So in this lecture, we have created a stack using Python list without size limit. So here we have created different operations for this stack and performed them to see how they are working in practice. Now in the next lecture, let's create a stack using Python list with size limit. In this case, we will have size limit for the stack, which means that we can insert only limited number of elements in the stack. So see you in the next lecture. Hi there, and I hope you have understood everything very clearly till now in this course. Now in the previous lecture, we have created a stack using Python list in which we don't have size limit. This means that we can insert as many as elements in the stack. Now here in this lecture, we will create a stack with limited size. This means that the maximum number of elements in the stack is predefined. So let's get started. So here again, I will create stack class. Then inside stack class, I will create init function. In this time, it will take self parameter and maximum size. As you remember in the previous lecture, when we create a stack without size limit, we don't have this parameter over here. But here we have this parameter. So here we will set self max size to the parameter that we are receiving from here. And then we will initialize empty list. So I'm not going to rewrite it here. I'll just copy and paste it over here from the previous lecture. So in the previous lecture, we have created this str method over here. Now with this, we have successfully created our stack data structures. So here we have only an extra element, which is max size. So in this case, the time complexity for this method over here is O1 and the space complexity is also O1 because we are just initializing an empty list over here. Now let's continue to the operations that we can perform on this stack over here. So the first operation is isEmpty method. So this method also is same as the one that we created in previous lecture. So I'll just quickly create it here because here we are not doing any additional step. If self.list is empty, it means that our stack is empty, so we will return true. Otherwise, we return false. Next method over here is isFull method. In the previous lecture, we didn't have size limit for the stacks. That's why we have not created isFull method. But in this case, we have size limit, so we need isFull method over here. So here I will create isFull method. So dev isFull. So it takes self as a parameter. So how do we know that if this list is full or not? So here, if length of list is equal to maximum size of stack, it means that this list is full. So we will return true. Otherwise, we will return false. It means that we can insert an element to this list over here. Here, the time complexity for this method is O1 because here we are just comparing two variables and returning true or false. So that's why the time complexity is O1. And it's clear that the space complexity is O1 also because here to perform this operation an additional memory is not required. So let's continue to create the next method. The next method is push method. So push method is responsible for inserting an element to the stack. So here I will declare push method like this. Push. So we know that it takes self and value parameter. So here we will have different case that we had in the previous lecture. So here first we need to check if the stack is full or not. So if self dot is full, it means that we cannot insert an element to this stack here because we have set maximum size. So we will return saying that the stack is full. Otherwise, here again we can use append method of list and insert an element at the end of this stack over here. And the value will be inserted over here. And after inserting, we will return saying that so the element has been successfully inserted. So with this we have completed our push method. So we know that the time complexity in this case is amortized constant because if we set the maximum size a bigger number and appending this list over here might take amortized time complexity, which means that it might reach ON time complexity. Now the space complexity to append one element is O1. Now here, before continuing to the next element, I want to check this stack if it is working properly or not. So here I will create custom stack based on the this stack class over here. Then first I will print out isEmpty method, custom.isEmpty. Then I will print out isFull method. Then I will push some element to this stack, then print out this stack over here. Now let's run our code to see how this is working. Here, when you are creating custom stack, you have to be very careful because we need to set maximum size over here. In the previous lecture, we were just creating this without any parameter, but here we need to set maximum size over here. So let's run our code. So when we run our code, we see that from the first method over here, it returns that it's true, which means that our custom stack is empty. Then it returns false, which means that it's not full yet. Then we are inserting 3 elements and printing out the custom stack. We see that as we insert, the element is located on the top of the previous one. So the methods that we created over here works very well. Now let's continue to the next method. The next method is pop method. So the pop method is the same as the method that we created in the previous lecture. Here I'll just create it very quickly. So here I've created pop method. So what we are doing over here is we are just checking this stack. If it is empty, we are saying that there's not any element in the stack. Otherwise, we are calling pop function of list, which is removing the last element and returning its value to us. So the pop method over here is same as the one that we created in previous lecture. That's why I'm not going in detail of this method over here. Now the pick method also is the same. Here, I'll just copy this and paste it over here because we know that pick method returns the last element from stack. So here again we are checking if the stack is empty. We are saying that there is not any element in the stack. If it is not empty, we will return the last element from the stack. So to return last element from the stack, we need to take length of this list over here and -1. So it's obvious that the time complexity for this method over here is O1 because we know that accessing any element of list takes O1 time complexity. Now the space complexity also is O1 because here an additional memory is not required to perform this operation. Now the last method in our case is delete entire stack. So delete method. So I will create delete method like this. So in this case we are just setting this list to none. So with this we have successfully deleted the stack from the memory. Now with this method we have completed our creation of stack using Python list in 2 cases. Now let's combine all these methods over here and see what is the space and time complexity for these methods in the stack in case of Python list. So here we have combined all these methods together. So let's see time and space complexity for these methods over here. So to create a stack takes O1 time complexity, because here we are just initializing an empty list. And for creating a stack using Python list takes O1 space complexity, because here we are not inserting any element to the list. That's why it takes ON. Let's continue to the next method. The next method is push method. So as we said before, when we are creating a push method, we are using standard functionality of Python list, which is append method. So in case of append method, the time complexity is amortized constant, which means that as we insert many elements in the list, the insertion becomes very time consuming, because here, as we insert elements, memory reallocation might occur. Now the space complexity for inserting one element is O1 space complexity. Now the next method is pop method. So pop method is responsible for removing last element from the stack and returning its value. So here the time complexity is O1, because in this case we are using standard functionality of list, which is pop method. So the pop method for list takes O1 time complexity, and the space complexity is also O1, because here we are just deleting an element from the list. Now the next method is pick method. Pick method is responsible for returning the last element from the stack. So we know that in case of list, when we access any element in the list, it takes O1 time complexity. This is the most efficient property of list. Accessing elements in the list is very fast. Now the space complexity for accessing element is O1, because here we're just returning the value of accessed element. Now the next method is isEmpty method. So isEmpty method also takes O1 time complexity, because here we are just checking the list if it is empty or not. So in this case, if condition takes O1 time complexity. Now the space complexity is O1 also, because here we are not doing any memory related operations. So the last operation over here is delete entire stack. So deleting entire stack also takes O1 time complexity, because here we are just setting list to none. So it takes O1 time complexity. Now it's obvious that the space complexity will be O1 also, because here we are not inserting any element to the memory. We are just deleting all elements from the memory. That's why it takes O1 space complexity. Now with this we have completed our creating of stack using Python list. Now in the next lecture, let's see how can we create a stack using linked list. So see you in the next lecture. Alright, in the last lecture we have learned the common operation that can be performed on a stack in the list implementation. Now in this lecture we will implement stack using linked list. So let's see how it works. To create a stack using linked list, firstly we need to create an object of single linked list class. So when we create an object of single linked list class, it basically creates a blank head. So the reference of head right now is null. So there is not any node in this linked list over here. So once we created a blank stack, the next thing that we are going to do, we need to insert elements to it, which is push method. So let's see how do we do that. So first we create a blank node and assign a value to it. Then we change the head reference to point to this node over here. So right now we have null in the head reference. So if we change the head reference to the physical location of this node over here, this element will be pushed to the stack over here. So as you see, as we update the head reference, the element is pushed to the stack. And right now, the next pointer of this node is null, because there is not any node after this node over here. So let's push one more element to this stack. In this case, we need to update the next reference of this node to point to the first node over here. And we know physical location of this node over here is 111. So we update the next reference of this newly inserted node to 111. Then we need to change head reference to point to this node over here. So we are updating head reference to the physical location of new node, and the link between head and previous node will be destroyed. By doing this, this element is inserted to the stack to the top of previous element. Then let's push one more element to this stack over here. So if you want to push a node to the stack, first we are creating a blank node, then assigning value to it. Then we are changing the next reference to point to the first node in the list. So in our case, 222 is the physical location of first node. So we are updating the next reference of this node to the 222. And then we are changing head reference to point to this newly created node over here. So by doing this, the reference between head and previous node gets destroyed. And then this element is inserted to the stack at the top of previous element. Basically, every time when we push a node to a stack, We are inserting the node at the beginning of linked list over here. So this is how push operation works in stack in case of linked list. Now let's see how the pop method works in a stack. So if we want to pop an element from stack, we know that the last entered element must be removed first. This means that in this case we need to remove first element from this list over here. Because when we push an element to the stack, in case of linked list, we are adding it to the beginning of linked list. So the first element is always the one which is inserted last. So in this case, if we call pop method, this node from here gets out. So pop method will return this node from here and it will remove this node from here. So to remove first element from the linked list, we just need to change head reference to the next. So if we update head reference to the next node, the link between head and the first node gets destroyed and this node is returned, and now there is no point to this node. It's eligible for garbage collection. So the garbage collector comes and deletes it from the memory and it gets out from the stack over here. Now let's call pop method one more time. In this case, this method will return this node over here. So once again, we will update the head reference to point to the next node, and the link between head and the first node gets destroyed and it returns this node, and there is not any point to this node. It's eligible for garbage collection. So the garbage collector comes and destroys from the memory and it's popped out from the stack. Now the next method is pick method. So we know that the pick method is return the top element in the stack. So in our case, the last element that is inserted to the stack is the first element in the linked list. This means that when we call pick method, it will always return the first element from this linked list. So to return the first element, we just need to return the head value. We know that head points to the first element, so the head value is the value of first node over here. Then the next method is empty method. So we know that this method checks if the stack is empty or not. So how do we do this in case of linked list? So we know that in case of linked list, if head points to none, it means that this linked list is empty. So this method will be like this. If head reference is none, it will return true, otherwise it will return false. Because if head reference points to the none, it means that we don't have any elements in the linked list. Then the next method is delete method. So this method is responsible for deleting stack from the memory. So to delete stack from the memory in case of linked list, we just need to set head reference to none. So by setting head reference to none, these elements from here will be destroyed one by one from the memory. So the stack will be deleted from the memory. Now this is all operations that can be implemented in the stack in case of linked list. So hopefully the logic behind them is clear now. Now in the next lecture, let's use Python programming language and create stack in practice using linked list. So see you in the next lecture. Alright, now in this video we will create a stack using linked list. So let's get started. So the first thing that we are going to do over here, we will create node class. So node class, inside init function, we will initialize value for this node. So by default it takes none. Then we are setting set self value to value and self next to next. So this is our node class to create a node and assign a value to it. Then the next class is linked list class. So I'll just quickly create this class over here as well. So this is our linked list class. So in this class we are just creating a head and setting it to none. Now we will start to create our stack class, in which we will use this linked list and node classes to create stack. Okay, stack class, we will declare stack class like this, stack, and inside init function we will create an object of linked list class. So by doing this we are creating a stack with only head value, and this value is points to none now. So there's not any element in our stack right now. So this part over here is responsible for creating a stack using linked list. Now the time complexity for this method over here is obvious that it's O1, because here we are just creating an object of linked list. And the space code complexity also is O1 because we haven't inserted any element to this linked list over here. Now the next method will be isEmpty method. We will declare it like this. So it takes self as a default parameter. Then how we are checking that if this stack is empty or not. So if linked list head value points to none, it means that this is empty. Otherwise there is element in it. So if self.linkedlist.head points to none, we will return true. Otherwise we return false. So now let's run our function to see that if this is working correct or not. Because in our case now it's empty, so it should return true. So I will create custom stack over here, which is an object of stack class. So by doing so, we are creating an empty stack. So let's print out the value that comes from the isEmpty method. Now we know that it's empty, so it should return true. So let's run our code. You see that the result is true, which means that our isEmpty method works perfectly. Now the time complexity for this method is also O1, because here we are just checking the head value, if it is none or not. So it's obvious that the space complexity is also O1, because in this case we are not inserting anything to the memory. Now let's continue to the next method. So we know that in case of linked list, we don't have isFull method, so we will not create isFull method over here. So we are continue to create push method. So push method takes two parameters as always. So we need to insert a value to this stack over here. So the first thing that we are going to do here, we will create a node and assign a value to it. And this value comes from this parameter over here. Then we need to change the next reference of this node to point to the first node in the linked list. So node.next will be point to self linked list.head, which is the first node in the linked list. Then we are setting head to point to this node over here. So self linked list.head needs to point to this node over here. So by doing so, we are inserting an element at the beginning of linked list. So let's see what is the time and space complexity for this method over here. So as always, we start from the first line. So the first line is we are creating a node and assign a value to it. And we know that this is a one-time complexity. Then we are updating the next reference of this node to point to the first node. And then we are updating head to point to this node. So this means that all lines of this push method takes all one-time complexity. So pushing element to the stack in case of using linked list is O one-time complexity. Now the space complexity is also O1, because here we are just creating one node in the linked list. So inserting a node at the beginning of linked list takes O1 space complexity. Now let's run our code to see how this push method is working in stack. But before running it, we need to print out the custom stack. So to print out custom stack, we know that we need to change str function in the stack class and in the linked list class. So in the linked list class, as we did before, we are changing the iter function, which makes our linked list iterable. So we use this function in the linked list section, so I'm not going to explain it in detail. This is just the same function, I just copied and pasted it over here. And this function makes our stack printable. So we use this function also in our previous lecture. So this function makes our stack printable in the way that stack should appear. So you just need to add these functions inside these classes over here. So let's see how push function works. So here I will call push function several times. Then we will print out custom stack. So let's save and run our code. So you see that every time when we add an element to the stack, the element comes to the top of the previous element. So first we inserted element 1, then we inserted element 2, then 3. So 2 comes to the top of 1 and 3 comes to the top of 2. So as you see, our push method works the way that it should be. Now let's continue to the next method. The next method is pop method. So let's declare our pop method. So it takes self as a default parameter. So the first thing that we are going to do over here is we will check if this stack is empty or not. So I will call if self empty. It means we will return saying that there is not any element in the stack. Otherwise, we will delete the first node and return its value. So here I will create node value takes the self linked list dot head value, which is the first node in our case. Then we are changing the head reference to point to the next node. So we are setting head to point to the next node over here. Then we need to return the value of node that we removed. So we know that we assigned the value of node here. So we will return node value. So if I save it now and run our code, we will see how it works. So here after push method, I will call pop method. After pushing elements to the stack, I will print out our stack over here. Then I will print dashes to see the differences. Then I will call pop method. Then one more time, I will print out our stack over here. So let's run our code. You see that after pushing elements to the stack, our initial stack was like this. Then the second version of stack is like this. So 3 is popped up from the linked list. So to see that if this is returning 3 over here, we can print out the return value of this pop method. So if I run our code, you see that 3 is returning over here, which means that pop method works perfectly. Now let's see what is the time and space complexity for this method over here. So the time complexity for this method over here is O1, because here first we are calling empty method which takes O1 time complexity, then we are deleting a method from the beginning of linked list. And we know that deleting an element from the beginning of linked list takes O1 time complexity. Now the space complexity is also O1 because here we are deleting one element from the stack. Now let's continue to the next method. The next method is pick method. So basically this method is similar to the pop method, so I'll just copy the code from here and paste it over here. But in case of pick method, we are not deleting an element from the top of the stack. So here I will rename it pick, and here we are checking if this is empty. We are returning that there is not an element in the stack. Otherwise, we will return the value of first node. So we know that when we push an element to the stack in case of linked list, we are inserting elements to the beginning of linked list. So this means that the first element is always the top element in the stack. So that's why we will return the value of first element in the stack. So this function returns the top element from the stack in case of linked list. So let's run our code for this function to see that's how it is working. So if we run our code, you see that it returns 3 because 3 is the top element in our case in the stack. Now let's continue to the last method, which is delete method. So I will declare it delete self. So to delete element from the stack in case of linked list, we will just need to set head value to none. So I will set self linked list dot head to none. So with this we are deleting a link between head and the first node, so the first node becomes eligible for garbage collection. Now then it gets deleted from the memory. Then it continues to the second node, third node, until it reaches the last node in the linked list. So with this we successfully delete a stack from the memory. Now the time complexity for the last method, which is delete method over here, is O1 because here we are just setting the head reference to none. And the space complexity is obviously O1 also. So with this method we have completed our operations on stack using linked list. Now let's combine all complexities of this method to see a big picture of time complexities of stack operation in case of linked list. So here we have combined all time and space complexities of stack operations to see a big picture of it. So the first operation over here is creating a stack. So we know that in case of linked list, to create a stack, we just need to create an object of stack class in which we are just initializing head value of linked list to none. So in this case, this takes O1 time complexity because this operation is not time consuming operation. Now the space complexity obviously is O1 because here we are not inserting any node to the linked list. We are just creating head reference and setting it to none. Now the next operation is push operation. So we know that in case of linked list, in stack, when we push, we are inserting an element at the beginning of linked list. This means that the time complexity will be O1 because here any traversing operation is not required. That's why we are just updating the head reference to point to this node, and we are updating the next reference of this node to point to the first node. That's why it takes O1 time complexity, and each time when we call push method, we are inserting only one element. That's why it takes O1 space complexity. Now the pop method also takes O1 time complexity because in this case we are returning first element from the linked list. And we know that to return the first element, we just need to return the value of head value. And here again, any traversal operation is not required. That's why it takes O1 time complexity. Now the space complexity is also O1 because here we are just returning the value of head and deleting the first node from the linked list. Now the next method is pick method. A pick method is responsible to return the top element from the stack. So in this case, we know that top element is located at the beginning of linked list. That's why it will return first element. So the time complexity will be O1 because in this case also any traversal operation is not required. So space complexity is also O1 because here we are not doing any space related operation. Now the next operation is isEmpty operation. isEmpty method takes O1 time complexity because in this case we are just checking the head value. If it is reference to none, we are returning true. If it is not reference to none, we are returning false. So this takes O1 time complexity. Now the space complexity is also O1 because here an additional space is not required to perform this operation. And finally, the last method is delete entire stack. So to delete entire stack, in case of linked list, we just need to set head value to none. Then the first node becomes eligible for garbage collection and it gets deleted from the memory. Then after deleting first node, the second node becomes eligible for garbage collection, and the garbage collector comes and destroys it from the memory. And it continues like this until it reaches the last element in the linked list. And this operation takes O1 time complexity, because here we are just updating the head reference to none. Now the space complexity is also O1, because in this case we are deleting all elements from the memory. So it's obvious that it will take O1 space complexity. This is all for this lecture. So in this lecture I have put all space and time complexities of stack using linked list to have a big picture of time and space complexity. Now in the next lecture, let's see when we need to use stack and when we need to avoid stack. So see you in the next lecture. So in the previous lectures, we have learned how can we create stack in 3 different cases. Now before concluding this section, let's see when we can use stack and when we need to avoid it. The first point is, whenever you want to implement LIFO functionality, then the stack is an ideal choice, because stack internally use this functionality, so we don't need to do any extra effort to implement LIFO method over here. So we know that LIFO method means last in first out. So here you can see that the last element that we inserted to the stack is 4. So to access the first element, first we need to remove this element, then second last element, then element 2, then we will reach element 1 over here. So this implements LIFO functionality. The second advantage of using stack, it cannot be easily corrupted, because here we cannot insert an element at the middle of stack over here. So the new element can only be inserted at the end of stack. Because of this restriction, the chance of data corruption becomes minimum. Now the biggest problem of stack is random access is not possible. It means that we can only access the last element in the stack. So if we want to access the first element in the stack, what will happen? We have to remove all elements from here, then we will access the first element in the stack. And as the data size increases, access problem becomes very costly, because all we have to do, we have to call pop method several times to reach to this element over here. So it will be very time consuming operation. Now with this lecture, we have concluded the section of stack. So hopefully everything is clear about stack data structure.